Afternoon. Can you all hear me?
Yes.
Thank you. It's 12:30. We'll get started here. So today our focus will be on proton NMR spectroscopy. I do appreciate you coming today. And first of all, I wanted to introduce you to the concept of chemical shift. And I had mentioned last time about how different kinds of hydrogen can absorb different radio frequencies. And that's really the focus here, is that when, and this is a better picture of that, these are the different kinds of hydrogens we're dealing with, and this is where they appear on the proton NMR spectrum. So you can see these bars here. So an H attached to a C attached to an O will tend to be around, say, this here, about 3 to 5 ppm. Oops, somebody's chatting, and what are they saying? Can't hear you, but everybody else can, I think, Julie. Can everybody else hear me?
Yes.
No, thank you.
Yes.
All right. Hopefully Julie will get that sorted. All right. So you can see here that the different places that these hydrogens will appear on the spectrum. And it makes it a pretty useful tool for being able to say, well, what kind of hydrogens are we dealing with in this molecule? I mean, that's not the only thing you can do, but that's an important It's an important part of it. So we call that chemical shift, and this value down here in ppm it's related to the radio frequencies that are used to figure out where these peaks are going to end up being from the compound. And that's also adjusted for the magnetic field that we're dealing with as well. So it doesn't matter what magnetic field we're dealing with for any given NMR spectrometer, they all come out to the same kinds of ppm values down here. ppm stands for parts per million, but that's not really something you need to be aware of. You just need to be aware of what's going on in this here. Yes, they can, Julie. Yeah, thank you. Thank you, folks. All right, so this is something you're actually going to be given, this correlation chart. You're also given this other bit of information too about integration and about multiplicity as well. So none of this is stuff that you actually have to memorize, but you do have to be aware of how to use it. Okay, so let's take a look at some of these other things here. All right, so we've got the chemical shift. There's a little bit of language that we use here with downfield and upfield, which is related to the magnetic field, and downfield is to the left and upfield is to the right. And I use that when describing peaks relative to other peaks. So I might say that a peak here is upfield from a peak that's over here, for example, or a peak is downfield. This peak is downfield from all these other peaks. That's how I might use those words here. So you can see that there's a bit of a trend going here as to where these different hydrogens appear. You'll have alkanes down here, that's CHs that are connected to other CHs. And then you've got CHs connected to Os. So as we add electronegative atoms, we tend to move downfield to the left. And then we've got hydrogens on double bonds and hydrogens on aromatic rings. Those appear more to the left as well. Then when we have atoms are electronegative and attached to double bonds, and it's even further down here. And then the ones that are furthest to the left are the ones where we have hydrogens that are parts of carboxylic acids. And you can see that's a C double bond O connected to an OH. So you can see the trends there in the correlation chart. Again, not something you have to memorize. It's given to you. The important point here is you get one set of hydrogen peaks for every different kind of hydrogen. So that's what I'm going to look at now. So let's say we've got a compound that looks like this, and I'm circling it here with my cursor. And you can see what I'm doing here is I'm labeling these A, B, C, D, E. You'll notice I don't label the C double bond O. Can anybody tell me why I'm not labeling that C double bond O?
Because it's already 4 things attached, 4 hydrogens.
Yeah, well, there's no hydrogens on it. Is it probably the
oh, that's what I said. That's
okay, yes. Okay, thank you, Victoria. All right, I didn't quite hear that last part. Yes, it's got no hydrogens on it. You see, the thing is that Proton Nmr only picks up one thing, protons, nothing else. So that's why I don't label that. But if I have a compound like this that isn't particularly symmetric, I've got 5 different kinds of hydrogen that I'm dealing with. Now you might look at this and say, hang on, I've got B, C, D here. They're all CH2s, but they're not related by symmetry. So no, those CH2s are all different from each other. So that's why I'm labeling them differently. So what I'd expect to see here is 5 peaks, 5 different sets of hydrogens here. But if you look at something below it, you can see that that's got a plane of symmetry right down the center. So this would only be expected to have 2 peaks. So you see symmetry is going to play a big role in how we look at these proton spectra. Likewise over here, we've got 3 different kinds of hydrogens. Again, a plane of symmetry down the center. And when you're dealing with aromatic rings, yeah, we have 3 different kinds of hydrogens here on the aromatic ring, but those will tend to overlap. That's their nature. They're really so close together that they're going to appear as one mess of peaks. All right, any questions so far? All right. So here's an example of a Proton Nmr spectrum, and you'll see that you'll have these groups of peaks, And often these peaks are split into smaller numbers of peaks. We'll get into that in a second. That's called multiplicity. And you can see the chemical shift, that's where the peak is located. And the other thing that's important, and we'll get to this in a bit, is going to be integration, which will allow us to determine how many hydrogens are actually responsible for that peak. But you can see what I've tried to do here with this spectrum is I've tried to overlay it with the correlation chart. So you see the 10 corresponds to the 10 and the 0 pretty much corresponds to the 0 down here. I know it's not quite, but near enough anyway. The point is that I know that this peak here that I'm circling with my cursor is going to be the aromatic hydrogens. And you can see that's where it appears on the correlation chart. The CH here is going to be the one that's connected to the bromine. And you can see the bromine down here. So I know that that's this one here. And then the other two they're going to be here, and you can see that set of peaks for each of those. So I'm just giving you that so you can get an idea about what chemical shift tells us. Any questions so far?
Yeah. Are the peaks in order? Like
No.
No.
No, they're not. It all depends on the environment that they're in, Julie. Do you see the CH2 here? This one that I'm pointing at?
Yeah.
It's kind of between the aromatic ring and the CH with the BR. So it appears actually downfield from the CH3, which is on the end. So that's the CH3, there's your CH2 here. So you see they're not really in order. It all depends on what's connected to those hydrogens, what's near them. And of course you'll get this correlation chart, so you don't have to memorize any of that. I wish it was that easy, but it isn't. Okay, so a lot of you have taken calculus. Can anybody tell me what integration tells you when you integrate something in calculus? What are you usually getting, on a practical basis? Any thoughts? I know a lot of you have taken calculus. Don't lie to me. I don't like being lied to. Anybody integration?
I took calculus but walked away with nothing from it, so I can't help you. I'm sorry.
Oh, okay. Well, that's unfortunate, Jonathan. There's a lot of good stuff in calculus.
It happened to me during COVID, so it went to online, so I got nothing either. But I'm going to assume integration is bringing two things together.
No. In integration, it gives you the area under a curve on a practical basis. Does that sound familiar at all, Sierra?
Yes, and doing integrals. Those were such a pain.
Yeah, you go. Yes. Yeah, well, that's what we're doing. All right. So, yes, I get your message, Morgan. That's, well, hopefully now you'll get something more from it next semester when you take it. So what we're talking about here is you can see that if you could measure the actual area under the curve, you could figure out how many hydrogens were kind of responsible for that peak. So that's what these numbers here next to the peaks are. It's kind of like the area under the curve. So 3H, 2H, 1H. Further, we can connect these to actual functional groups or groups of hydrogens. So 3H is generally a CH3. Shock and awe, huh? A 2H could be a CH2 or an NH2. A 1H could be a CH, NH, or OH. And then you've got combinations of these as well. 9H is like 3 CH3s, but they all have to be the same environment. Well, 6H can be 2 CH3s and 3 CH2s, and I'll show you how you can distinguish between those two groupings. And the 4H is generally 2 CH2s, but again, they have to be related by symmetry. The other clues that we can get here is when you've got a 2H peak, if it's a single peak, it's likely an NH2. If a 1H is a single peak, it's generally an NH or an OH. Right, so we'll get to that in a bit as well. In the 7 to 8 region, we've got a special set of peaks. Those are your aromatic rings. You can see that here, 7 to 8 ppm. And a 4H peak is generally an aromatic ring with 4 hydrogens on it, and a 5H is an aromatic ring with 5 hydrogens on it. Now, why might that be useful? Well, let me show you. If you've got a 4H aromatic ring, yeah, this is just between 7 and 8, by the way. This is what an aromatic ring looks like. If you've got, let's say, 5 hydrogens, we'll put in 5 hydrogens. How many spaces are left on the aromatic ring for things to connect?
1.
1. Isn't that fantastic information? Whee! All right. What about if we have a 4H? How many spaces then? 2.
Is it always a 6-sided aromatic ring?
Yes, always.
Because some of
Without
your
exception.
exercises had smaller, like had ones with 4 sides and 3 sides.
No, when you get, well, I'm not going to talk about that now, but when you take organic 2, we'll get into that. But we're just talking about your garden variety benzene ring here.
Okay, so there's not going to be any other ones.
No, I guarantee it. May lightning strike me down, Julie.
Okay,
Lightning
those are all
strike
witnesses.
me down.
You know,
Yeah,
one of
okay.
these days you're gonna regret saying that.
No, I'm not, because I never say it. I never say it and expect it. You know, you can take it to the bank, Jonathan.
Because there are some that you have on your list of exercises that are others that aren't 6-sided. You know that, right?
Not aromatic rings, sunshine.
Maybe they're called something else. I don't know. They're in the answers to the NMR exercise. Or no, they're the IR exercise.
That's IR. Ha, 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 ha. That's a different
That's a
kettle
different rules.
Different kettle of fish.
Okay.
Hey, I'm being honest here. I'm trying to be as transparent as I can.
Okay.
All right.
It's appreciated.
I know. All right. Any other questions so far? This information, you're given this. It's part of the. You see it? It's part of the the sheet that you're given. There you go. Your integrations right here. So you don't have to memorize that either. See it right there. Yeah. Yeah, I recommend whenever you're doing anything with NMR, have this sheet in front of you. Otherwise, it's kind of like trying to cut down a tree without turning on the chainsaw. Sorry. Wait for that to disappear. We'll go back to where we were. There we go. Any other questions about integration and what that tells us? So here's an example. It's what I had said earlier. So we've got the 5H aromatic ring here. We've got the 1H, which is this CH here connected to the bromine. We've got the CH2, which is the CH2 here. And we've got the CH3, which is the 3H over here. So 3H is the CH3, 2H is the CH2. Anybody got any questions? All right. Multiplicity. Now, multiplicity, if you look at these peaks here, you'll see, I know they're not very well resolved, but you can see that these peaks are actually multiple peaks. Like this one here is 2 peaks, this is 2, and this one is actually 6. I've got clearer pictures of these coming up, so don't panic. But that's multiplicity. So what does multiplicity tell us? This is the hardest part. Multiplicity tells us how many hydrogens there are on adjacent carbon atoms to the hydrogen that we're talking about. I know it sounds really complicated, doesn't it? But here's the rule. If there are n peaks, we have n-1 adjacent hydrogens on carbon atoms, where HX is the actual HX that the peak is responsible for. So that's the rule. Let's take a look at some examples of this. Let's focus on the 1H over here. So I said that the 1H is this one here that I'm circling with my cursor. You all can see my cursor, right? Yes?
Yes.
Good, good. So that's the hydrogen. So here's the rule. If there are n peaks, let's see, it's 1, 2, 3, 4, 5, 6. See, there's 6 peaks there. That means there must be 5 adjacent hydrogens. So let's see. Now, we don't count the hydrogen we're actually talking about, right? So we're looking at hydrogens on adjacent carbons, and here they are. 1, 2, 3, 4, 5. And by adjacent, I mean next to. So we've got the CH, and then we've got hydrogens connected to Cs next to the CH. And that would be responsible for these 6 peaks. N peaks, N-1 hydrogens on adjacent carbons. Take a look at the CH3. That's this boy over here. All right, that's CH3. How many hydrogens are on carbons adjacent to the CH3? Well, look, there's 2 peaks, so I'm expecting 1 adjacent hydrogen, and there he is, right there. So this is the CH2, the 2H, and again, 2 peaks, so that means 1 adjacent hydrogen, and there it is right there. So you're getting a picture of how, if we know how many peaks there are, we can figure out where in the structure a certain hydrogen might be. Isn't this fun? Isn't this already fun?
Professor Musgrave.
Yes, Philip.
So I get what you're saying, but for like another problem where you would have maybe like 5H or like 9H, do you have an example of that, of what that would look like?
Well, all I can tell you is that we only really go up as high as 7 peaks, generally speaking. We can go higher than that, but generally we're really focusing on just up to 7. And what that means is, if we're talking about CHs here, so we can talk about 1 peak would be 0 adjacent hydrogens, and that might be 0 adjacent hydrogens on carbon. And you'll notice that's a CHX connected to O, even if that's an OH. And look here, CHX connected to NH. See, the NH doesn't see, because this is only for hydrogens on adjacent carbons. This doesn't count for anything that's not on carbon. And that's really important as well. But Philip, you'll get plenty of other examples of these as we go through the compounds, okay?
Okay.
And this one here, CH connected to a C double bond O, that'll appear as a single peak as well. So when I say HX, it could be H1, H2, H3, it really doesn't matter as long as they're all the same hydrogen. So that's multiplicity, and I'll take this back here to what I had said earlier, the NH2 and the OH. So let's talk about that a little bit. So let's say we've got this compound here. The spectrum is going to look something like this. And we'll do another one over here. So it'll be a 1H, this will be 2H, and this will be 3H. So if I was to label this, you should be able to say that the peaks responsible for each of these would be A, B, and C. Is everybody okay with that so far? Anybody have any questions? Just about how I know which peak is which for A, B, and C. Is everybody okay with that? All right, well, nobody's saying nothing. So
just to confirm, because the 3H is the CH3,
yes.
the 2H is the
Yes.
CH2, and the 1H has to be the OH in this
Yep.
case.
Yep.
Okay.
Yep.
All right.
Yeah, don't overthink it, Rebecca.
Okay, just simple.
All right. So let's look at the multiplicities here. Let's focus on the 3H here. How many peaks do you see here on the 3H? And that's
3.
It's 3, yeah. So that means there must be 2 adjacent hydrogens. What do you know? There are. You can see them there. But look at the CH2. That's got 4 peaks, so you're expecting 3 adjacent hydrogens. And it's only hydrogens on carbons that we count. We don't count this one because it's on an oxygen. So the CH2 here can see the CH3, but it can't see the OH. And likewise, the H on the O can't see the CH2 either. So that appears as just a single peak. So all of this multiplicity talk that we go on with, and I make it very clear here, tells how many hydrogens are on adjacent carbon atoms. And it's really important that we talk about carbon atoms. They're the only ones that these other hydrogens can see. Now you'll also notice when we talk about these multiple peaks that there's a certain pattern to the way that their intensity is set out. Oh gosh. Okay, I'm going to show you something here. Does anybody know what I'm doing here?
Christmas tree?
It's not a Christmas tree.
Oh yeah, it's that
Pyramid.
pyramids, that calculus thing. It's the
Do you know what it's called?
I forget, but it was a pain. It was a pain in the neck when I did it.
You would add like the 2 numbers and get the bottom one, and it was just weird.
Yeah.
Pascal's triangle. Oh god, I hated this thing.
I feel like everybody hated it.
You want to hear something funny, Musgrave? Your laugh sounds like the evil laugh of Michael Jackson's Thriller.
Oh, really? Oh, wow, that's a real throwback, Philip. I think there's a lot of people here who have no idea what you're talking about.
Yeah.
But you know, they should. I mean, that's classic. That's classic. Yes. All right, so if you've got 6 peaks, then the intensity of those peaks is going to be 1:5:10:10:10:5:1. And that's what I'm talking about down here. Let's see if I've got, here we go. So you got 1:5:10:10:5:1. So you get this nice even progression. I'll give you just a very small background on how that works. If you've got a coin, it's going to be heads and tails, right? Let's say we've got 2 coins. Can anybody tell me the possible combinations that we could have for 2 coins?
Heads,
I
tails,
hated statistics.
Tails, heads, 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 and tails, tails.
All right, so you got heads, heads. We got
Heads, tails.
heads, tails. One more.
And then
Tail
tails,
heads.
head.
Whoops. See, 1 to 2 is to 1, and you know, if you increase the number of coins, then we come up with all these different combinations. And yeah, this would be the 1 is to 2 is to 1 combination that I'm looking at here. Oh, I know. You do this in statistics. I know you do. I know you do. But there's 2 spins on a hydrogen. It can be up or down. So that's why we get all these different combinations of the way these hydrogens can multiply. Is multiplicity, how they sort of see each other. But again, it's only hydrogens on carbons. So that gives you an idea at least of what's going on. So if you've got three peaks, a 3 peak is going to look like this. Oh, actually, I've got it up here. So you got 1 to 2 is to 1. All right. Any questions?
Yeah, I'm not sure why that's relevant.
Well, if you've got a grouping of peaks and it didn't look even, let's say it looked like this, I'd begin to think it wasn't due to this sort of coupling that we're talking about, or this sort of multiplicity. It has to be that kind of nice even progression is what I'm getting at.
So what else would it be then?
Well, take a look at this peak here. Do you see that nice even progression going on with this mess of hydrogens here? No, you don't, right? It's a big mess of peaks. So that would tell me that we have a lot of overlap going on, because you've got a lot of hydrogens that are similar to each other, but not quite the same. So they're all coupling, but we're getting a whole mess of peaks that are all coupling together and overlapping.
Is that because they're in the aromatic ring and they're more in movement and not as stable?
No, it's not so much about stability. It's about the fact that these hydrogens are very similar to each other. So the peak positions are very close.
Okay.
So we get a lot of overlap.
Okay.
That's more what it's about, Rebecca.
Okay. I did have a question when you, just before you started Pascal's triangle, and I didn't quite get this in the lectures, but when the OH, it doesn't see the CH2. So where it's a 1H peak, it should have 0 hydrogens next to it.
Yes.
And because it's OH, we don't count the hydrogens that are next to it?
Correct.
Okay.
Yeah, because it doesn't see, the hydrogen on O doesn't see the hydrogens on C, and the hydrogens on C don't see the hydrogens on O either. It's like there's a big wall there. They just can't see each other.
Okay. In either direction.
Correct.
Okay.
Yeah, the O is kind of like a wall. I don't know exactly the reasoning for it, but it just seems to block everything.
Okay.
N does the same thing.
Okay.
So it's only hydrogens on C's that are going to be useful for this whole multiplicity thing.
Excellent. Okay.
All right, any other questions? So those 3 concepts that we just dealt with, chemical shift, integration, multiplicity, those form the foundation of interpreting NMR spectra. All right, that forms the foundation. So how do we solve structures? Now, what you'll be given is always a molecular formula and an NMR spectrum. An NMR spectrum will consist of all these peaks, and it will also show you the integration as well. So there's a 7-step process that I use in order to figure out the structure of a compound given the molecular formula and an NMR spectrum. The first step is doing what we did the other day, and that was figuring out the double bond equivalence. So determining how many rings or double bonds there might be in the compound. So for this one, C5H10O would be the same as C5H10. If it was saturated, it'd be C5H12. 12 minus 10 divided by 2 is 1. You'll get used to doing this the more you do it. So I know this compound has 1 ring or 1 double bond, but I don't know anything else yet. The next thing we do is we identify the pieces we can actually see. And yes, sorry, go on.
When you say it has 1 ring or 1 double bond, if it had a ring, the ring would have no double bonds inside it?
Correct.
It would just be a ring because it would count as 1
yes.
double bond. So it could conceivably have a ring with
At this point, yes.
Oh, okay.
Because we don't have any other information.
Okay.
But we're about to get a whole lot more.
Okay.
All right. Step 2, we look at the pieces we can see based on the integration. So all I'm doing here is saying, well, that 2H, that's a CH2. 3H, that's a CH3. 2H, that's a CH2. And 3H, that's a CH3. Anybody lost so far? Any questions? All right.
Wait, so the so the 3H is the would be the HO then, right?
Say it again, please.
The 3H would be the HO because of the single peak.
No. No, that doesn't follow. All I'm talking about here is the integration, Philip.
Yeah.
Yeah. What I had said earlier is that if it's 1H is a single peak, it's probably an OH.
Okay.
Now, this is, I think, the most important step, and it's a step that people don't like to do. I've been told that for some people, they say, well, look, I can't do it. It's against my religion. I don't really believe it, but, you know. Now, you'll notice, I'll go back up here. Do you remember I had said for this compound here, I didn't label the C double bond O because it didn't have any hydrogens on it? Well, the implication there is that the C double bond O can be in the compound, but obviously you don't know it's there because You don't see it in the spectrum, right? Because there's no hydrogens on it. So there's got to be a way for us to figure out if the C double bond O is present, but we can't do that just by looking at the spectrum by itself. So the technique that I like to use here is a subtraction technique. So what I do is I have the pieces that I can see and I subtract them out from the molecular formula that I have here, the C5H10O, and then I ask myself what's left over. So the idea is if you subtract everything you see from the entire thing, all you're left with are the things you cannot see in the spectrum. So in this instance, what's left? You've got a C, an O, and a double bond equivalent, because you know the double bond equivalent isn't in the CH2s or the CH3s, so it must be in the part you can't see. So if you've got a C, an O, and a double bond equivalent left over, that would indicate you have a C double bond O. And again, the reason the C double bond O doesn't appear in the spectrum is because it does not have a hydrogen on it. But it's still very important to figure out that it's there. Does anybody have any questions?
Yeah, maybe I just missed something, but from looking at our spectrum, there weren't any 1H's. So wouldn't that mean that had to be a double bond O?
Well, I don't think that would follow, Jonathan. The fact there were no 1H's.
Well then, how? But there's no way for there to be 2 H's on an O.
That's true, especially when the O has already got 2 bonds on it. O can only have 2 bonds.
Right. So if there's no 1H's in the spectrum, it would have to be a double bond O.
Not necessarily. There could be an O between 2 C's, right?
Yeah, that's a good point.
But it's single bonded, so no, so I don't think that necessarily follows. But when you've got a C and O and a double bond equivalent left over, then you can say, yeah, you definitely for sure you've got a C double bond O.
Okay, that makes sense. Thank you.
All right. Does anybody have any issues with step 3? Any questions about it? I just want you to understand it. That's all. I just want you.
What does DBE stand for again?
Double bond equivalence, Sierra.
Oh, okay.
Which means rings or double bonds. And remember,
Gotcha.
in step 1, we determined that there was 1 double bond equivalent.
Can you repeat that part about the C double bond O, like how you can see that you have a C double bond O?
All that's left is a C. Do you see C5? And count up C's, 1, 2, 3, 4. That's 1 C left, right?
Yeah.
The O, there's no O's in here, so there's an O left over. And we haven't, none of these contain the double bond equivalent, none of these groupings. So all that's left is a C, an O, and a double bond equivalent, which means that what's left is the C double bond O.
Okay.
Is that all right, Keisha?
Yes.
That's going to be a very common thing that you'll see, by the way. So what that means is the structure is going to be made of everything we see, which is the CH3, the CH2, the CH3 and CH2, and what we can't see, which was the C double bond O. So then we have to put that together. And there's really only 2 ways that I can put that together. Excuse me, there's this one, the top one, and the bottom one. Now the top one, if I put it together this way, will have 4 peaks. And the bottom one will only have 2 peaks. Now, I know from my spectrum I've got 4 peaks, so I already know which one it is. It would have to be this top one here. Now, you can see here that I've got these lines here. Well, the way I figure out that is that I know that carbon has 4 bonds. So if it's a CH2, it's got 2 more opportunities to bond. A CH3 has 1 opportunity to bond, and the C double bond O has 2 opportunities to bond. And then when I put them all together, those are the only 2 ways that I can put them together, are these 2 right here. 4 peaks because there's 4 different kinds of hydrogen, 2 peaks because there's 2 different kinds of hydrogen. So then what I can do is I can verify the structure by looking at each of these and assigning them. And the way I'd assign them is say, so Philip, you remember you were talking about that single peak? Well, that's that's a 3H, that's a CH3, and the CH3 responsible for that single peak is the one next to the C double bond O because it's not next to any hydrogens. So 1 minus 1 is 0, so 0 adjacent hydrogens to the CH3. So D must be this CH3. That makes A the CH3 on the other end, which has 3 peaks because it's next to 2 hydrogens. And then you've got the B peak here, which has 6 peaks, so it's adjacent to 5 hydrogens. 3 plus 2 is 5. And the CH2 number C, that I've got lettered C, is next to 2 hydrogens, and so it appears as a triple peak over here. All right, any questions?
Yeah, I have a question.
Mm-hmm.
I'm not sure, I don't know that it's that important in the end, but I'm not sure about how you're getting different peaks, because you're deciding whether it starts from an up to go to a down and make a peak, or you're just, or from a down to an up, but that doesn't really affected by, I mean, you could legally move that CO over to the next peak and still have the same amount of peaks.
Oh, I don't see it. No, I don't agree with that, because if you move that over, the situation would be like this. It would be CH3, CH2, C double bond O, then CH2, and then CH3. But the issue then would be that you have 2 different kinds of hydrogen, so you only see two peaks, not 4 peaks like we're seeing here.
But I mean, you can draw it any way you want though, right?
Yes, you could, that's right. As long as it's got the same connectivity as I see here, yeah. I mean, you could put the C double bond O where the CH2 is that what you're saying? We can switch those around?
Well, if you did that, it would be the same exactly.
It would be the same thing, yeah, that's right, that's my point.
But if you put it up above on the other CH2, the drawing would still look the same as far as peaks. You're saying
Would it? I don't think so, I disagree. If you move the C double bond over to this CH2, then this would be the structure you get, Julie, which has symmetry and only 2 peaks. So it does matter. This is the only structure I can draw where the multiplicities and everything matches up.
Okay.
Any questions? Any other questions?
Yes. Back to the to the step 1 that you had there.
Mm-hmm.
You had C5H10, and then you had O went to C5H10, and then you added like two extra hydrogens to the hydrogen. How did that go from H10 to H12?
What we're looking for is what it would be if it was saturated. And we use
Okay.
this formula here, CnH2n plus 2.
So
5, 2 times 5 plus 2.
So will it always just be plus 2 then?
No, it's 2n plus 2. So 2 times the number of carbons plus 2.
Where's that formula at? Is it in the PowerPoint or?
It's going to be on your. Let's go take a look at the. Hang on, let me get past Zoom here for a second. It's down the bottom here, Philip. This is on the sheet that you're actually given, units of unsaturation, and it tells you here. It gives you directions. Tells you how to apply different heteroatoms like halogen, nitrogen, or oxygen. And then down here it says you figure out how many hydrogens it would have if it was saturated, and it gives you the formula down here, CnH2n plus 2.
Oh, okay, thank you.
And then it gives you an example of how to apply that for something like what we have up here.
Okay.
You see, it's for C7H13 NF2O3. The O you ignore because it doesn't have any effect. Nitrogen, you subtract 1 hydrogen.
From the H.
Yes, from the H's you have, so that'd become 12.
And then because F is a halogen, you add 2.
You add 2. So
Okay.
it becomes C7H14.
Okay, thank you.
And then you can see it would have to be C7H16 if it was saturated. So 16 minus 14 divided by 2 is 1.
All right.
So you have that. You won't have to memorize it. I mean, it's right there. Okay, you'll have it on that sheet. It's going to be attached to your test. All right. Any other questions? Other questions? Just basic questions that I'm after here. Okay, so that's everything in a nutshell. I want to show you some neat things, some neat resources I have to help you with this. Not only are there examples in the Blue Book that are similar to what we just went through, I actually went to the trouble of doing some programming in JavaScript to come up with a little app that allows you to actually figure out what's going on. Actually, let's not do that. Let's do this instead. So down here in the test 4 folder, I have this folder called Proton Nmr Exercises, and the link I'm directing you to here is my Proton Nmr Exercises with Structure Builder. It's a really good tool for understanding how to solve NMR problems. And as far as I know, I'm the only one who's ever done this. So go to Proton Nmr Exercises with Structure Builder. There's a video on how to use it, and these are the 75 problems. I created 75 of these suckers for you to work with. I'm just going to pick one at random. I'll do number 36. Give it a second to load up here, especially the first time you do it. It's not quite loaded up yet. There we go, now it is. Now you might have to reduce the screen size here, so Control plus or Control minus. And why isn't that working? Oh, Command. Let's try it. There we go. That's better. Okay. So the first thing you do is you look at the molecular formula here. This one's C6H12O, so that would be 1 double bond equivalent. If you get the double bond equivalent wrong, it'll tell you it's wrong. Let's put in 4 just for kicks. See, it says DB incorrect. Try again. So it says the double bond equivalents are correct, so you can continue. So you select the pieces below and you watch the molecular formula count down as you click the pieces. So this is kind of like the subtraction step. So you click that and then you click that over here. So let's look at the pieces. So you've got a 1H here, that's likely a CH. So you find a CH, it looks like there's just one CH here. So we say CH by 1. So you see it, the piece will appear over here, but look at what happened to the molecular formula. It took away a carbon and a hydrogen. And then we've got 3 CH3s. So you've got 1, 2, 3. So 3 CH3s. And there they all appear here. And then there's 1 CH2. So what's left over? A C, an O, and look over here, a double bond equivalent. Oh, that must be a C double bond O. So there's one of those. And then you check the pieces to make sure they're okay. And they're right. And then what you can do is you can drag these pieces down here. The anchor piece goes on the anchor. And then you can come up with the correct structure based on what you're seeing here. So for this one, I think it's the CH3 goes next to the C double bond O for that one. And then you'll have the CH, CH2, probably the CH3 over here. And I'm actually going to make this the wrong structure. And you can see what happens. And if you put in the wrong structure, you hit submit, it says incorrect, please move the pieces and try again. And then you submit. Oh, there it is. And this here, if you, let's say you got it by trial and error, then you can, and you're not sure how you actually got the right answer, then click on here for a video solution. And I actually go through and explain exactly how you come up with that structure. This one is C6H12O. It has one double bond. Yeah, I programmed this. I did from scratch.
Good job.
Thank you, Deanna. I appreciate that. It was not easy. I'm going to say that. It was not easy. So anyway, there you go. You got 75 of those suckers that you can do. And it's I don't know, it's almost fun once you get into it. And if anybody tells me, oh, look, Dr. Musgrave, I'm really struggling with NMR, I'm just going to direct you to this. Because, you know, you can use it to pretty much understand it, in my opinion. Sometimes it makes it a lot easier. All right, so the link to that, is in the Proton Nmr Exercises folder, and you can find it down here. I also have this NMR guide, which is kind of handy as well. And it goes through all of the concepts, sort of summarizes them all in one document. So it has the peak shapes. Also, it gives a nice way of being able to tell if you've got a 6H peak, whether it's 2 CH3s or 3 CH2s. And what we usually find is if it's 2 CH3s, it's either a single peak, a double peak, or a triple peak. And if it's got four peaks, it generally tends to be 3 CH2s. So that's going to be advice that you can use as well. So that's in the NMR guide. I go through that whole thing about adjacent NH, OH, and NH2 groups and how they only appear as one peak. And ordering of ester groups, how you can tell which way they go based upon the chemical shifts. So there's a whole lot of good advice here. So let me go through that briefly here, the ester groupings. So if you've got this possibility where you're not sure whether it's C double bond O connected to O or whether it's O double bond connected to C double bond O, what you can do is you can use one piece of evidence, and that is the fact that CHs connected to Os generally appear at 4 ppm. So in this instance, when you've got, let's say we've got this structure here, we're not sure which way it goes. We know what's at 4 ppm, and that's the CH2. So if the CH2 is at 4 ppm, that must mean it's connected to an oxygen. If it was the CH3 that was connected to the oxygen, it would be at 4 ppm, and that would be the structure. So you can see the difference between these two. The only difference is that we switch these two things around. So I bring this up because this is often a point that students ask about. How can you tell which way this goes? And it's all about what appears at 4 ppm, because that's the thing connected to the single bonded oxygen. Does anybody have any questions? Okay. All right, so that's this is all in the Proton Nmr Exercises folder. All right, let's take a look at test questions, and we can get an idea of what you're going to see there. There's going to be 2 such questions on the test. So let's look at this one, fall 2019. Excuse me. So you've got questions 4 and 5. So, if you're thinking about just blowing off the NMR questions on the test, well, I think you're going to end up not feeling very good about yourself. Let's go through this one here. All right. So the first thing you would do, we've got C8H16O2. Somebody needs to mute. I'm hearing an echo. That'd be C8H16. And if it were saturated, it'd be C8H18. Philip, do you see how I get the 18?
Yes.
Okay. So 18 minus 16 divided by 2 is 1. So we expect 1 double bond equivalent in this compound. The next thing I do is I figure out how many pieces, what pieces I can actually see. So I'm kind of going to show you and combine that here. So these are the pieces I see. I see a 3H, that's going to be a CH3. I see a 1H, that's going to be a CH. It's not a single peak, so it can't be an OH. The only way that the 1H could be an OH is if that was a single peak, which it isn't. We've got another CH3 over here for 3H. And then we've got a 9H, which is going to be 3 CH3s. Now you might be wondering, how do I know that? Well, you've got this integration sheet or its integration section of the reference sheet that we're talking about down here that will tell you exactly what that is. So see 9H is 3 CH3s. Anybody have any questions? The other thing you'll notice is a little bit subtle. Where are we? Here we go. It's a little bit subtle, but I put the 3 CH3s underneath each other because they're all the same. They must be in the same environment. Now I know this. I know this because they're all under the same peak, so they must all be related by symmetry. So this isn't just 3 random CH3s I can put anywhere. They all have to be related by symmetry somehow. Okay, any questions so far? All right, here's what I want you to do. I want you to tell me what would be left over. Okay, so figure it out. I'll wait here for a second. Do the math here, tell me what's left. I'm going to give you a hint. The hydrogens will always work out because we see every hydrogen. So there's no way we can't see a hydrogen. You don't even have to check the hydrogens. You only have to check the carbons and oxygens here. So I want you to tell me what's left over, what we haven't accounted for.
2 C's.
There's 2
Oh.
C's.
Yeah,
2
C.
carbons, 2 oxygen.
Two carbons and 2 oxygens. That's good so far. Okay, 2 carbons and 2 oxygens. Anything else we haven't accounted for?
1
DBE.
All right. So what I'm going to do is I'm going to take the leap that the DBE is going to be a C double bond O. So what's left over is a C and an O. What else do we know about this C here? And this is really important. What do we know about this C since it's left over?
It doesn't have a hydrogen.
It doesn't have a hydrogen on it. If it had a hydrogen on it, we would have seen it. Yes. Right. So now you're seeing how powerful it is to do this subtraction step. Because without doing the subtraction step, you might not have known this C even existed. That's why it's so important.
Is it also true that the O has no hydrogen?
Yes.
Because we've already accounted for all of the hydrogens?
Yes. Yes. And if we did have an OH, wouldn't it have appeared in the spectrum as a single peak?
That's right. Okay. Yep. Mm-hmm.
So we know it's an O that doesn't have any hydrogens on it. That adds to the mystery. But what's interesting here is when you've got a C left over and you've got these 3 CH3s, we can kind of account for that automatically by doing this. So that accounts for the CH3 groups and the C. So 3 CH3s in the same environment connected to that C. And then we can try and put the rest of it together. You'll notice we've got a CH here. How many peaks do you see there on the CH? Can anybody tell me? How many peaks do you see there?
Looks
It
like
looks
4.
like 4.
It's 4, yeah, it's 4. That means there must be 3 adjacent hydrogens, so the CH must be adjacent to a CH3. You'll also notice there's a CH3 here that's got 2 peaks, so that must be adjacent to 1. So we've accounted for this CH and this CH3. The only thing we haven't accounted for here is the C double bond O and the CH3. And the only way this works out now is if I put the C double bond O here and put the CH3 over here. CH3 is a single peak, so I can't put it next to the CH, for example. See, it's a single peak. So it must be next to the C double bond O. So that would be the answer to this one.
We have the O too, correct?
Oh, the O. Oh, yes. I was just testing you all. Yes, that's right. So the O. Oh, yes, the O. No wonder where he goes. Well, look over here. What's at 4 ppm? The CH3. So we know then, I'm going to go ahead and delete that. Since the CH3 is at 4 ppm, it must be connected to the oxygen. So the oxygen must go directly in here. So that would be the correct structure. The O couldn't go down here because if it did, then it would be the CH that would be at 4 ppm, and it isn't. What's at 4 ppm is the CH3. Anybody got any questions?
So for this question, we just have to draw the structure?
Yep, the correct structure is here.
Okay. Well, yeah, obviously.
I grade it pretty hard too, I've got to say, because it's either right or wrong. People who know what they're doing tend to get it right, and people who don't know what they're doing tend to get it wrong. I wonder how one could figure out what they were doing. Well, you do that, you do those exercises I showed you. And I think it really helps with being able to solve these kinds of problems. You see, it was interactive. You could move pieces around, and you could do the same kind of thing here. All right, does anybody have any questions? I'll show you one other thing that is kind of useful. Actually, no, I'll show you one thing that's kind of useful in a second once we do another problem here. All right, so for this one, it's C13H18O2. If it were saturated, sorry, no, if it were, if we just take into account the oxygen, C13H18. Now, if it was saturated, Philip, I'm going to put you on the spot. You asked me earlier, what would it be if it was saturated? C13H what? You there, Philip? If you're not there, it's okay. I'll get someone else. All right, does anybody want to tell me?
28.
28. Is everybody okay with 28? Okay. 28 minus 18 divided by 2 is 5. So 5 double bond equivalents. Now, if you remember what I had said earlier, 4 double bond equivalents would account for a ring. So what that tells me, an aromatic ring, I should say. So what that tells me is this compound contains an aromatic ring and then 1 double bond somewhere else. So that's pretty powerful information. Now, I also do have this 5H grouping up here in the aromatic region, so that's just more proof that we have an aromatic ring somewhere in the compound. Does anybody have any questions?
The leftover double bond equivalent couldn't be just a ring, not aromatic? It only can be a double bond?
No, sorry, it could be a ring or a double bond somewhere else. Yeah, I was spoiler alert. Sorry, Rebecca.
Okay.
It's most likely a double bond. But you're right, it could have been a ring. So the 5H in the aromatic region is going to be, I'm just going to draw this as a circle here, and you can do that for an aromatic ring. It's going to be an aromatic ring with 5 hydrogens on it. And yes, Julie, it does have to be a 6-membered ring. So that's what we're seeing over here. Can anybody tell me what this 2H represents here? What kind of grouping? Anybody want to guess?
CH2.
2H. Sorry?
Is it a CH2?
It's a CH2, yes. And the other 2H, that's another CH2. And I have a 6H. Now, he's a single peak. He could be 2 CH3s or 3 CH2s. But what I had said earlier, the odds are, if it's a single peak, it's most likely 2 CH3s. It's very difficult to have a single peak and have 3 CH2s. By the rules of symmetry, it just is very unlikely for that to happen. So I'm going to put that down as 2 CH3s because it's a single peak. That's what experience is going to teach you as you go through this. And then we've got another CH3 over here. All right, so if I do my math here and I figure out what's left over, we've got 13, then we've got 6, 7, 8, 9, 10, 11. So we've got 2 C's left over. We've got 2 O's left over. And that's 4 double bond equivalents there. So we've got 1 double bond equivalent left over. So I'm going to say that we have a C double bond O. So it's the same situation pretty much as before. Does anybody have any questions?
Are there hydrogens left over? 3?
Nope.
5.
So let's see. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 6 is 15, and 3 is 18.
I see what I did. No, I counted the 3 CH3s as 6 instead of 9. Okay, thank you.
Now, I understand the hydrogens will always work out because we always see all the hydrogens. That's the nature of NMR. You don't even need to check the hydrogens every time. So now we have to put this sucker together. All right, what are we going to do? Well, let's start at 4 ppm this time. And you can see we've got this CH2 that's at 4 ppm. I'm going to say that that's connected to an oxygen because it is at 4 ppm. That's going to be my starting point. Now look at how many peaks there are. How many peaks do you all see for CH2? How many peaks? There's 3, right? So how many adjacent hydrogens? Remember, it's 1 less than the peaks you see. 2 adjacent hydrogens. So that CH2 must be adjacent to another CH2. So the CH2 that we're talking about here, we've already taken account of, and it must be next to this other CH2. Now look at how many peaks the CH2 has. How many peaks do you all see here for this CH2?
6.
6. 1, 2, 3, 4, 5, 6. How many adjacent hydrogens for this CH2?
5.
5, 1 less. So this CH2 is next to a CH2 and a CH3. Probably this CH3, the one that's got 3 peaks. So we've accounted for that as well. So what's left over? We've got an aromatic ring, bare C. We've got the O figured out here as well. C double bond O and 2 CH3s. So there's not really very much left over. So I'm going to do a C double bond O here. And if I put these 2 CH3s connected to the C, and then I've got the aromatic ring here, that would probably work out. So I think that's everything that's been, taken into account after that. So the aromatic ring has to go on an end because it's only got one join point, and that pretty much leaves us with that structure. Does anybody have any questions? You're not going to understand how to do this straight away. The only way you'll get to understand this is by practicing it. And I've given you the perfect tool to be able to practice this. It's not something you want to walk into on test day and say, I'll just wing it. And I'll just see if I can get the right answer by guessing it. I just don't feel like that's a winning strategy for anybody. The only way out is through. The only way out is through. You have to do it. You have to go through it. All right, any questions?
I think at least for me, the hardest part is seeing or figuring out where the DBEs come from, like trying to figure out how many there are and how you can tell in the picture.
So is it the actual calculation you have issues with, Sierra, or?
Yeah, that part's a little confusing and how it changed from 4.
The 4 here is just the aromatic ring part. It is actually 5. But because we know that the whole thing contains 5 and that 4 of them must be due to an aromatic ring, there must be one double bond or ring left over. In this case, it was a double bond.
And how do you know there's an aromatic ring?
Because anytime you've got 4 or more, you can always say 4 is going to be the aromatic ring.
Okay.
Because it's got 1, 2, 3 double bonds and a ring. That makes up the 4.
Gotcha.
Okay, so that's just going to be a general thing that you can do. It just makes life so much easier. If you can just say, well, automatically, there you go, 4 double bond equivalents, that's a ring. Okay, any other questions? Some people catch on to this a lot quicker than others do, is what I've noticed. Some people latch onto it straight away like a duck in water. Other people tend to drown initially and then they give up, which is unfortunate. But everybody can understand it.
I have a question.
Yes.
So when we're answering this on the test, this is the way that you want it set up. Like we don't have to draw this into a different structure.
Oh, actually, I don't really care how you do it, Keisha. This is just my way of coming up with the structure. All I'm expecting you to do is come up with a structure.
Okay.
A correct structure.
Okay.
In the mini lecture, you were also going through and assigning A, B, C, D.
Oh, yes. Yes.
Is that part of this question or no?
It is actually, because it does say assign the peaks, right?
Okay.
And I did forget to do that. But yes, so what you would do is you could put letters on each of these for each different one. So it'd be A, B, C, D. And you can only assign hydrogens, obviously. And then for this particular one, I'll just kind of draw a little facsimile of it down here. The assignments would be, this would be A, B, C, but we don't know which is which there. The CH2 with the 3 peaks, that's E. The other CH2 is F. the single peak is going to be the two CH3s, which is D, and then the other CH3 at the end, that's G. So that's a good way to check that you've actually got the right structure, if you can make up assignments that make sense on the actual structure you come up with. Now, for another thing here, I'll just point this out, maybe last thing before we adjourn here. I've got this cut out pieces for NMR, so this is probably a good way to practice it. You can print this page out as many times as you like, and then you can cut these pieces out and use that to help you figure out the structure. It's not on the test, but when you're practicing it. So there's that. And then I've actually got the answers to all these NMRs as a PDF document as well, with the peak labels. See, this used to be a Flash thing. I did it, well, I didn't do it somebody else did it in Flash. I had to reprogram it in JavaScript because Flash is dying. Flash is going away at the end of the year. And the school wouldn't do it for me, so I had to do it myself. But you can see here, it's all set up with all the letters and everything. So that's good practice too. All right. Any other questions? Okay, so if anybody is in my, well, a lot of people are in my lab today. I'm hoping that you'll all be there and you'll be able to follow along with what I'm doing. All right, so I will see you all later on. Thanks for coming.
Thank you.
Thank you.
Yeah.
Sierra, Philip, Isabella, do you need anything?
No, I'll see you in lab. Thank you.
Okay, no worries, Sierra. Philip? Isabella? Okay.